Today I will discuss about capacitor. Capacitor is that electrical device which can store charge. Now suppose this is a body and it is charged with positive charge. Now if we add some charge, then its potential will be increased. Now we can say that charge stored by this body is directly proportional to the potential of the body. So Q is proportional to V and Q is equal to CV. This constant of proportionality is called capacitance of the capacitor. Usually we use capacitor which have a positive object and another negative object. As a result, the positive charge and negative charge field lines start from positive charge and end at the negative charge. As a result, positive charge will be attracted towards the negative charge and both the charge hold in this device. So, in case of capacitor, we use two objects, one positive and one negative. Both are given equal charge. That means Q are equal for both the object. Now we want to calculate the capacitance of a sphere, conducting sphere. Suppose this is a sphere of radius r and this sphere is charged by Q. Q is the charge of the sphere. Now we know that potential at the surface of the sphere V is equal to Q by 4 pi epsilon 0 into R. Therefore Q is equal to 4 pi epsilon 0 R into V. Therefore this part, if we compare with the relation charge and potential, then we can say that Q is equal to CV. Therefore C is equal to 4 pi epsilon 0 into R. Now if we consider two concentric metallic spheres separated by very small distance, that is difference of the radius of two spheres are very small. Suppose this is radius of the inner sphere is A and radius of outer sphere is B. Now if we consider another concentric sphere of radius R, now we are giving plus Q charge on the outer sphere and minus Q charge on the inner sphere. Therefore now we have to calculate the field due to this negative Q and positive Q on the sphere of radius R. This is a Gaussian surface of radius R. So Q in is equal to minus Q and S is equal to 4 pi R square. Therefore, for surface integral E dot ds is equal to Q in by epsilon 0 is equal to Q minus Q by epsilon 0. And E is constant at every point of the sphere of radius R. So we can say that closed integral of E dot ds is equal to E into 4 pi R square is equal to minus Q by epsilon 0. Therefore, E at this point is equal to minus Q by 4 pi epsilon 0 R square. Now V is equal to integration E dot dr minus. So potential difference between inner sphere and outer sphere is A to B. Limit will be from A to B is equal to minus A to B minus Q by 4 pi epsilon 0 R square into dr is equal to A to B Q by 4 pi epsilon 0 1 by R square dr is equal to Q by 4 pi epsilon 0 minus 1 by R A to B is equal to Q by 4 pi epsilon 0 1 by A minus 1 by B is equal to Q by 4 pi epsilon 0 B minus A by AB. So we can say that Q is equal to 4 pi epsilon 0 AB by B minus A into V. So it is clear that this part is the value of the capacitance of the capacitor. So C is equal to 4 pi epsilon 0 AB by B minus A. Now in case of cylindrical capacitor, there are two coaxial cylinders, inner cylinder having radius A and outer cylinder radius of outer cylinder is B. Now inner cylinder is given a charge of minus Q and outer cylinder is given a charge of plus Q. Now, if we consider a Gaussian surface which is also a coaxial cylinder between these two, suppose R is be the radius of the intermediate cylinder, this R, and this will be the ideal Gaussian surface, and charge enclosed in the Gaussian surface Q is equal to minus Q. Therefore, flux phi is equal to minus Q by epsilon 0, and that is equal to closed integral E dot ds. It can be split into three surfaces, one to circular faces, E dot ds, two circular faces, suppose C is a circular faces, and E dot ds of curved surface. Now it is clear that all the flux crossing the curved surface normally, that is direction of the field and direction of the surface S in the curved surface is parallel, but direction of the circular face and the direction of the electric field is perpendicular to each other. So you can say that integration E dot ds of circular face is equal to 0, and therefore minus Q by epsilon 0 is equal to E into ds of curved surface is equal to E into area of the curved surface is equal to 2 pi R into H. H is the height of the cylinder. Therefore, E is equal to minus Q by 2 pi epsilon 0 R into H. Now, V is equal to integration minus E dot dr, and the limit is A to B is equal to A to B minus plus Q by 2 pi epsilon 0 RH into dr is equal to Q by 2 pi epsilon 0 H integration A to B 1 by R dr is equal to Q by 2 pi epsilon 0 H into ln 1 R A to B is equal to Q by 2 pi epsilon 0 H ln B by A. V is equal to. Therefore, Q is equal to 2 pi epsilon 0 H divided by ln B by A into V. So you can say that C is equal to 2 pi epsilon 0 H divided by ln B by A. Now, most popular capacitor is cylindrical capacitor and parallel plate capacitor. This is two parallel plate, and we will consider a very long parallel plate. One plate is given positive Q charge and another plate is negative Q charge. Now it is clear that all the charges are in the facing surface, that means inner surface between the two parallel capacitors. So if the area of the parallel plate be A, then surface charge density is equal to Q by A. Therefore, field, we know that in case of plate, if we consider two long sheet, then flux are normal to the sheet and it is independent of the radius. So we can say that field lines starting from positive, therefore field inside to parallel plate is E is equal to sigma by epsilon 0 is equal to Q by A epsilon 0, and potential difference is equal to V is equal to integration E minus E dot dr is equal to Q by A epsilon 0 into dr is equal to Q by A epsilon 0 into D. D is the separation of the plate. Therefore, we can say that Q is equal to A epsilon 0 divided by D into V. Therefore, C is equal to A epsilon 0 divided by D. Now, unit of capacitance. SI unit of capacitance is farad, and if we write the formula C is equal to Q by V, then 1 farad is equal to 1 coulomb per volt. But it is very large unit. In practice, we usually use microfarad is equal to 10 to the power minus 6 farad or nanofarad. Nanofarad is equal to 10 to the power minus 9 farad. Now, combination of capacitors. First, capacitors in series. Suppose there are three capacitors connected in series. So the three capacitors and there's a battery. Potential difference of the battery is equal to V. Now the value of the capacitance of the capacitors are C1, C2, C3 respectively. So the charge stored at the first plate of the capacitor is equal to plus Q. Therefore, due to this plus Q charge, minus Q charge will be induced at this part on the other plate. And since the whole section is neutral, so the first plate of the second capacitor will be plus Q and this will be minus Q. Again, this is plus Q and minus Q. So we can say that in series, all capacitors store equal quantity of charge. So charge Q is constant in all capacitors. But the potential difference PD is different, and that depends on the value of the capacitance of the capacitor. Therefore, we can say that potential difference across C1 is equal to V1. Say this is the potential difference across C1. This is say V1, and this is V2, and this is V3. So V1 is equal to Q by C1. And V2 is equal to Q by C2, V3 is equal to Q by C3. And the total potential difference across the plate of the battery is equal to V, which is equal to V1 plus V2 plus V3. Now, equivalent capacitance. So, we are imagining one capacitor, a single capacitor, which can store Q charge against potential difference of V. This is equivalent capacitance of the series combination. So we can say that V is equal to C Q by CE is equal to Q by C1 plus Q by C2 plus Q by C3. So equivalent capacitance E is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now parallel combination of capacitors. When two or more capacitors are connected in such a way that all the capacitors get equal potential difference, or potential difference between the plates of individual capacitors are same, then we can say that that is parallel combination of capacitors. Suppose in this combination, suppose capacitance of the capacitors are respectively C1, C2, C3, and charge stored in first capacitor Q1 is plus Q1, this is minus Q1, plus Q2, minus Q2, plus Q3, and minus Q3. Potential difference between the plates is V for each capacitor. So in case of parallel capacitor, potential difference is constant for all capacitors. Second, charge stored in each capacitor depends on the capacitance. And the total charge is sum of charges of individual capacitors. Therefore, total charge stored Q is equal to Q1 plus Q2 plus Q3. Now, if CE be the equivalent capacitor, equivalent, that means it will store Q amount of charge when connected with V potential difference. So we can say that CE is the equivalent capacitor into V is equal to C1 into V plus C2 into V plus C3 into V. Cancelling V from each side, we will get CE is equal to C1 plus C2 plus C3. In case of parallel, individual capacitance should be added to get the equivalent capacitance. Now, during calculation of different problems in capacitor, few steps are to be followed. Suppose this is a capacitor and is capacitance is C and charge stored is plus Q at this and minus Q at this plate. If it is point A and this is point B, then VA, that is potential at A, minus Q by C is equal to VB. So when we move from positive plate to negative plate, potential will drop, and during calculation we have to follow this method. VA minus Q by C is equal to VB. We can apply the principle of Wheatstone bridge in a circuit of capacitors also. Suppose there are 4 capacitors. In this way, if we connect 4 capacitors in such a way that potential difference between C and D is 0. Therefore, we can say that means galvanometer deflection will be 0, no deflection of the galvanometer. So we can say that VC minus VD is equal to 0. That implies VC is equal to VD. Suppose plus Q1 charge stored in capacitor P minus Q1 plus Q2 minus Q2. Now the potential difference between C and D is 0. So we can say that Q1 is equal to Q2. So we can write it as this is Q1 and this is Q2 minus Q2 plus Q2 minus Q2. Now, if we move from point A towards C, then VA minus Q1 by P is equal to VC. Again, if we move from A to D, then VA minus Q2 by R is equal to VD. But VC is equal to VD. Therefore, we can say that VA minus Q1 by P is equal to VA minus Q2 by R. VA cancel. Therefore, Q1 by P is equal to Q2 by R. Therefore, Q1 by Q2 is equal to P by R. Now, if we move from C to B, VC minus Q1 by Q is equal to VB, and VD minus Q2 by S is equal to VB, and VC is equal to VD. Therefore, we can say that Q1 by Q is equal to Q2 by S. That implies Q1 by Q2 is equal to Q by S. From this relation, Q by S is equal to P by R. So P by Q is equal to R by S. Therefore, capacitance of the capacitor P and Q, PQ and RS, if they are related in this manner, then potential difference between C and D will be 0. We usually use this principle in solving different problems. We have to find out the Wheatstone bridge inside the circuit, and it is given there is a capacitor between C and D. Since there is no potential difference, so the capacitor between C and D will not hold any charge, so we can neglect that capacitor. In that case, we can calculate the equivalent capacitance by series combination of P and Q, series combination of R and S, and these two series combinations are in parallel. In this way, we can calculate the problem. So it becomes very easy. Now, energy stored inside the capacitor. Energy stored inside the capacitor. Suppose this is a capacitor and it is given a charge of plus Q in one plate and another minus Q another plate, and capacitance of the capacitor is equal to C. Then we can say that the duration Q is equal to CB. Now a very small charge is added to each of the plate. Then this small charge, if dq be the charge, then the work to be done is equal to dq into V against the repulsive force, because dq is positive and we are adding dq charge in the positive plate. Therefore, work done against the repulsive force is equal to this, and W is equal to dW is equal to dW. Therefore, W is equal to minus V into dq from 0 to q is equal to minus 0 to q. V is equal to q by c into dq is equal to minus 1 by c q square by 2. Therefore, potential energy stored U is equal to minus W. So, therefore, U is equal to half q square by c. If we convert q into V, then we can write it c square v square by c, that is equal to half cv square. And if we convert c into q and v, then u will be equal to half q into v. So, energy stored inside the capacitor is equal to half qv is equal to half cv square is equal to half q square by c. Now, we are considering a capacitor of capacitance C, and it is connected with a battery to a switch. The potential difference of the battery is V. This is positive, negative, positive, and negative. Now, when we close the switch, charge will start moving from positive plate to the positive plate of the capacitor. Now, the role of the battery is it collect the charge from the negative plate, that is from this side, and transfer it to positive plate. So, the charge which stored in the capacitor will be transferred through the battery. Therefore, energy lost by the battery, is equal to Q into V. But energy stored in the capacitor is equal to half Q into V, and the remaining half energy which is given by the battery is converted into heat. So, heat produced during charging is equal to half Q into V. This is very important. So, energy consumed by the battery is QV, energy stored by the capacitor half QV, and energy that converted into heat is equal to half into Q into V. Now, role of dielectrics in capacitor. Suppose this is a capacitor, parallel plate capacitor, and this is a dielectric slab between the capacitor. Suppose plus Q charge is given in this plate and minus Q charge at this plate. Now, we have discussed in early video that some charge will polarize the dielectric slab. So, there is a minus charge, and this is plus minus charge, and this is plus minus plus minus plus, and remaining charge, the field lines will continue through the dielectric. So, surface charge density of the plate sigma is equal to Q by A. Surface charge density of the polarized, this is polarized charge. So, surface density of the polarized charge is equal to QP by A. So, Q free, that is difference between these two, which produce the field inside the dielectric, that sigma free, say F is equal to sigma minus sigma P. Therefore, F is equal to Q by A minus Q P by A is equal to Q minus QP by A. And the field inside E is equal to Q minus QP by A epsilon 0. Therefore, potential difference between the dielectric slab is equal to Q minus QP by A epsilon 0 into D. And we know that E is equal to E0 divided by epsilon R, that is dielectric constant or relative permittivity. Therefore, we can say that E is equal to E0, that is Q by A epsilon 0 into epsilon R. The potential difference V is equal to Q by A epsilon 0 epsilon R into D, because we know that V is equal to minus E dot dr integration. So integration of dr is equal to D, that is the distance between the plates or the thickness of the dielectric. Therefore, Q is equal to A epsilon 0 epsilon r by D into V. So we can say that it is equal to C A. We know that A epsilon 0 divided by D is equal to C0. That means capacitance when there is no medium, that is in vacuum. If these two plates are placed, then the capacitance is equal to A epsilon 0 divided by D and epsilon r into C0 B. So the role of dielectric, C is equal to C0 into epsilon r. So we can say that epsilon r can be defined as ratio of C by C0. That means capacitance of the capacitor when there is a dielectric slab divided by capacitance of the capacitor when there is no medium between two plates. This is a relative permittivity or dielectric constant. Now another thing, polarizing field that is sigma p by epsilon 0. This is a polarizing field EP. EP is proportional to E, that is the field inside the dielectric slab. So then constant of proportionality is equal to chi susceptibility. Now this chi is called susceptibility, and we know that EP is equal to E0 minus E is equal to chi into E, and E is equal to E0 divided by epsilon r. Therefore E0 will be cancelled, then we will get 1 minus 1 by epsilon r is equal to chi by epsilon r. So 1 is equal to chi by epsilon r plus 1 by epsilon r. So epsilon r is equal to 1 plus chi. This is very important. Now the force between two plates. Suppose positive plate and this negative plate, plus Q is stored at this plate and minus Q is stored. Capacitance of the capacitor is C. Therefore the energy stored, potential energy stored is equal to U is equal to half Q square by C. And we know that del U del X is equal to minus F. And the del X is the distance of separation. When there is no charge, there is no potential energy stored inside the capacitor. So we can say that F is equal to half Q square by C into D, and C is equal to A epsilon 0 divided by D. So CD is equal to A epsilon 0. Therefore F is equal to 1 by 2 Q square by A epsilon 0. We can prove it in this way. We can also prove this in other way. That is, if we consider this is a long charge sheet having charge plus Q, therefore E is equal to sigma, that is surface charge density, by 2 epsilon 0. And the force F is equal to Q into sigma by 2 epsilon 0. We know that force is equal to charge into electric field is equal to Q into sigma is equal to Q by A into 2 epsilon 0. So half into Q square by A epsilon 0. So we can prove it in this way. Now suppose there is a parallel plate, two parallel plates filled with dielectric slab of dielectric constant epsilon r or K. Now the capacitance of the capacitor C is equal to half A epsilon 0 divided by D. D is the separation between the two plates. Now if plus Q charge is given to the plates and the potential difference across the plates are constant, so we can say that energy stored inside the dielectric is equal to half CV square. Now if we slightly displace this dielectric slab to a distance x from its mean position, suppose this is x distance Now the resultant capacitance of the capacitor is equal to C dash is equal to A. Suppose we know that plate of this area of this plate A is equal to length of this into breadth. Breadth remain constant, but length, a part is evacuated and another part still have dielectric medium. So we can consider two capacitors connected in parallel. One have area B into X into epsilon 0 by A epsilon 0 divided by D, and another B into L minus X into epsilon 0 epsilon R divided by D. And this C is equal to, C can be written as L into B epsilon 0 epsilon R by D. Therefore, we can say that new capacitance C dash is equal to B into epsilon 0 divided by D into X plus epsilon R into L minus X. That is B into epsilon 0 by D X into 1 minus epsilon R plus epsilon L into epsilon R. Now the new potential energy will be according to this, that is U is equal to, U dash is equal to half B epsilon 0 divided by D into X into 1 minus epsilon R plus L into epsilon R into V square. And previous it was half into L into B epsilon 0 epsilon R divided by D into V square. Therefore, change of potential energy del U is equal to 1 by 2 D B epsilon 0 V square. So the common part of these two, remaining part X into 1 minus epsilon R plus L into epsilon R. This will be minus, minus and minus, and plus epsilon R to L. Therefore, B into epsilon 0 V square by 2D into minus X into 1 minus epsilon R. This is the change of potential energy. We know that force is equal to del U del X is equal to B epsilon 0 V square by 2D into epsilon R minus 1. F is equal. So this force will be act upon the dielectric slab, and this can be treated as restoring force. So the direction of the force will be this direction. F is equal to in this direction, and the magnitude of the force is as derived.